to us. We have so far studied something about rotational dynamics. That is, we studied the rotational kinetic energy, and the nice thing about that is through that we introduced the concept of rotational inertia, which replaced the concept of mass in in rotation. And it turns out the rotational inertia is more complicated than just mass. It has to do with not only the mass of the object, but where the masses are distributed. Okay, in general, the further the mass is distributed away from the axis of rotation, the more rotational inertia something has, which means the ability for it to resist angular acceleration increases. But exactly what causes angular acceleration? Okay, we're going to continue with this discussion of rotational dynamics. To do so, again, we look at the analogy between rotation and translational motion. In translational motion, what causes a linear acceleration? Of course, that's a force, right? To be specific, an external force. So, what causes the angular acceleration if it's a rotational motion? Well, we look at a very simple example. Suppose here's a door. That's the hinge of the door. How do you open up the door? Well, the door is initially not moving, right? And as you start rotation, you're actually giving it an angular acceleration so that it can start rotating. What you do is you grab the door handle and you push it. Okay, so you push it with a force, F, and then things start to rotate. So it acquired an angular acceleration. Now, if this is the hinge of the door, you don't see a door designed such that the hinge is here, do you? I mean, the doorknob is here. Because obviously, if you push it here, you're going to have a very hard time opening up that door, right? So if you do the same exact force here, it doesn't give you nearly as much effectiveness as the force there in terms of opening the door. So what did that tell us? Even though these two forces, the green and red one, have the same magnitude, they do not give you the same exact amount of angular acceleration. A force here is far more efficient in producing the angular acceleration than a force there. So what is the difference? They have the same magnitude, right? So what's the difference? This force is acted further away from the axis of rotation, and that one is very close. As a matter of fact, if you push right on a hinge, in other words, the distance between that force and the hinge is 0, or the axis of rotation is 0, you're not going to be able to start the door rotating at all. Okay, so you see, when it comes to producing angular acceleration, we need a quantity, we need a force, of course. But that force alone doesn't tell you the story. We also want to know where the force acts upon. Okay, and from this example we see the further away a force acts away from the axis of rotation, the more efficient, the better it is to cause angular acceleration. From this discussion, you know, it makes sense to define a quantity which depends not only on the force, but also on the distance between the force and the axis of rotation. Okay, that distance, we call it the lever arm. So how is lever arm defined? Suppose I have a force. Okay, suppose I have a force, F, and that force is in a certain line, which is called a line of action. That's called line of action. And I have a point O. If I want to know the effect of this force in causing a rotation about that point, you know, the force alone doesn't tell you the story. You have to also figure out the distance between that axis of rotation and the force. Just like here, the distance between the force and the hinge. Okay, so let me draw that distance out. It's the distance, perpendicular distance, okay, from the line, from that point of interest or the rotational axis to the line of action. That is called a lever arm. Okay, the lever arm is distance between here and there, which sometimes called R perp. Why perp? Because it's perpendicular to the line of action of the force. Obviously, in terms of the effect of this force causing rotation, the greater the force and the greater the lever arm, the better. So it makes sense to define this quantity tau, which is the product of F and R perp. Okay, this quantity is called torque. In fact, torque, just like force, is a vector. But what we have here is only the magnitude of the torque. We're going to see the full vector version in the next chapter. So, if force causes linear acceleration, what do you expect torque to do? Well, it's going to cause angular acceleration by analogy, right? So we're going to see what a torque is capable of doing. Okay, we have here an object in rotation, a rigid object in rotation. This is the axis of rotation, O. Let me consider one small mass of that object. This little mass is called, the mass is m. This force, F, is the net force exerted on this mass here. And the distance between the object and its axis of rotation, we call it R perp. It's perpendicular to the direction of motion. Okay, here's the direction of motion of the object. Because it's doing a circular motion, right? Direction of motion, V. You know, this force has two components. One is radial component, the other is a tangential component. The radial component serves what purpose? Well, it forces the object to do in a circular motion, right? It's a centripetal, it provides a centripetal acceleration. And that, of course, does not speed up or slow things down. But we're interested in angular acceleration. That is, how fast, or how does it speed up, does it slow down the rotation? That, of course, has to do with whether the speed of the linear motion increase or decrease, not the direction change. So we're more interested in this component, the tangential component of the force. Okay, we're interested in this component, F tangential. But you know, F tangential is perpendicular to this radius. So when you combine F tangential and R perp, isn't that just the torque that we talked about? The torque exerted on this mass from this force? In fact, this force has another component going in, right? That component is not of interest. In fact, it doesn't provide any torque. Because look, that force, that component of the force pushes directly into the axis. If you push the axis directly, are you going to cause the thing to rotate about the axis? Of course not, right? Try to push the hinge of a door directly. Does that open or close the door? It doesn't. So it is only this component that we are concerned about. And that, it is, as we see from the previous definition, it is the torque exerted on this object. So what can this torque do? Well, let's see now. According to Newton's second law, the tangential force exerted on this mass is equal to the mass of the object times what? The rate at which its speed changes, dv dt. Okay? dv dt. Not the whole velocity, but just the speed portion of the velocity. This is what makes it slow down or speed up. Meanwhile, this v is the linear speed of this object doing a circular motion. Let me rewrite it in terms of angular speed, because we know omega is the same for the entire object, so that makes things a little easier. So v equals omega times r perp. All right, plug that in. It's a rigid body, and therefore r perp is not going to change. This object always the same distance from the center of rotation. So let's plug that in. When you do ddt, r perp is a constant, so this becomes m ddt of omega r perp, and r perp is a constant. I'm going to take that out, m r perp d omega dt. Okay, what is d omega dt? Isn't that just alpha? Right? That's alpha. Okay, let's plug that in to here. See what we get. I get m r perp alpha. And there's one r perp here, another one here. You square it. That equals torque. So for this mass m, I find the torque exerted on it equals its mass times r perp squared times alpha. Now r perp is the distance between the axis of rotation and that mass. The reason why we use the perp here is because I want to keep the same symbol as the previous the previous discussion. This is a direction that's perpendicular to the tangential motion. Okay, so we call it r perp. But this is the torque exerted on this one mass, which is a portion of the entire object, right? Now what if I consider all the torques provided by all the external forces on the entire thing? Then I have to sum over all the individual torques. On that side, I have to sum over all the masses as well. Okay, so at this time, I'm going to give it a subscript I, so that it can sum over all the masses. Subscript I. So I have an I here, and I have an I here. this is torque on the i's mass. Alpha doesn't require a subscript I because alpha is the same for the entire rigid body. Let me now sum it up. Okay, I'm gonna sum over all the masses of the entire rigid body. Okay, on this side, what do I get? On this side, that's just the net torque on everything. Okay, let me not. At this point, we're not going to use a vector symbol, just scalar. Let's look at what happens on the other side. What do you have here in this parentheses? MIRI squared. Isn't that the rotational inertia about that axis? Right? So that's just I. See? That's just I. The thing in the red parentheses. And what's left is alpha. So that is what we get. Torque equals I alpha. There we go. This is called the torque theorem. Okay, the torque theorem. It's a theorem because we derive it from Newton's second law. It is also called Newton's second law for rotation because it looks just like Newton's second law, except you replace torque, replace external force with external torque, you replace I with mass with I, and you replace linear acceleration with angular acceleration, right? Instead of F equals ma, I have torque equals I alpha. And this is the perfect, extension of the analogy that we started out from kinematics. You look at the difference between, analogy between one-dimensional translational motion and fixed axis rotation. I have torque equals I alpha to replace F equals ma. So again, mass is replaced by rotational inertia. Linear acceleration replaced by angular acceleration. I have something new now. Force is replaced by torque. So this formula, the torque theorem, is conceptually very clear. It replaces Newton's second law for translational motion. It is more convenient when we study rotation to say that torque equals I alpha instead of F equals ma, because every portion of that rotation object may have different A linear acceleration, but they all have the same angular acceleration with a rigid body. So torque equals I alpha. I is therefore rotational inertia. This term makes perfect sense now because with the same torque, if I is large, you get a smaller alpha. So I represents the ability of an object to resist any change in its rotation, which to produce angular acceleration. Okay, a greater rotation inertia would mean a smaller angular acceleration given the same torque. That is the so-called torque theorem. Now, we have studied torque theorem for rotation, and of course we also have F equals ma. We still have F equals ma for translational motion, right? Is it possible for us to combine the rotation and translational motion to study an object which has both rotation and translational motion? Well, the answer is definitely yes. We're going to look at this very useful example.